Okay, we're going to do a little bit on proportionality. I will make sure at the beginning of next year that we do a little bit of some lesson starters on this as well. You should have met proportionality before, so if y is proportional to x, then y equals kx for a constant k. So all we're doing is just relating this into rates of change. So if the rate of growth increase of theta is proportional to theta, the rate of growth is to theta to t, it's proportional to theta, so that equals k theta. If the rate of decrease of theta is proportional to theta, then d theta to t is minus k theta. So that k is a constant, and we take k to be bigger than 0. And so if you get a negative here, you know that it's a rate of decay and not a rate of increase, because k is positive. If k could be negative, then you won't know whether the overall sign is positive or negative. Inverse proportionality, so if the rate of growth is inversely proportional to theta, then d theta dt is k over theta. And if the rate of decay is inversely proportional to theta, then d theta dt equals minus k over theta. So these rates of change, the rate of change in theta is d theta dt. Right, you might want to screenshot and make notes, but I'll keep going. I've written it all out already. So a few examples so you can get the hang of it. And yeah, apologies, lots of words on these. For algebra, as you can tell. So at time t, the area A of a circular patch of mould is increasing at a rate proportional to the square root of its area. So this is a typical kind of maths real life example. So we have a circular patch of mould, and it's increasing at a rate. So dA dt is proportional to the square root of its area. So that's the differential equation connecting A and T. So you're basically turning that sentence into a bit of maths with this. Right, second example. So I'm hoping it is that one. Sorry, I've lost the two. So this one here, I did see this on an exam paper somewhere. So the rate of decrease of the radius of a mint is inversely proportional to the radius. So it's just turning that into maths. So it's a rate of decrease of the radius of the mint. It's decreasing, so it's minus, and it's inversely proportional to the radius, so minus k over r for that one. And then the third one, we've got liquid being poured into a container at a constant rate of 30 centimetres cubed per second. So this is a change in volume, and it's leaking out at a rate proportional to the volume of liquid present. And so to model that as a differential equation, it's the volume that's changing. So if you're pouring into a container at a constant rate, you're changing this, the volume is increasing. And so the rate of change in the volume is equal to 30, so that's the increase from the liquid being poured in. And then it's leaking out at a rate proportional to the volume of the liquid present. So 30 minus kV. And we'll go on to solve these. That's kind of where we're heading with them. We can solve them with integration, but that's the next step. And then last one. So question 4. Sorry, I've lost a bit of wording on that one. So the temperature of a room is 18 degrees C. A cup of tea is left to cool in the room. The rate at which the temperature of the tea decreases is proportional to the difference in temperature between the tea and the room. So we're looking at a rate of change in temperature. So that's d theta, no, you said dt. d theta dt is the rate of change in temperature of the tea, and that's equal to, it's decreasing. So it's minus k, and it's proportional to the difference in temperature between the tea and the room. So that's theta minus 18. So to find a difference, you subtract, and you want it to be a positive difference here if you think about it, because then you know whether this overall sign is going to be positive or negative. And then a bit more information enables you to find the value of k. Remember, k is a constant, so it's fixed. So initially the temperature of the tea is 98 degrees C, and it is cooling at a rate of 0.5 degrees C per second, and we want to find k. We don't actually need the initially here particularly, but it just means that at a particular instant in time, these two are linked in this way. The temperature of the tea is 98 and the rate of cooling is 0.5. So 0.5, but it's a rate of cooling, so it's negative 0.5. So if it's cooling, d theta dt will have a negative gradient, if you think about it. And that's equal to minus k, lots of 98 minus 18. And then solving that, we get k is equal to, excuse the decimal fractional mix, 0.5 over 80, and so k is equal to 1 over 160, and k is fixed at that. K should be positive, so if you end up with a negative k, it might be that you've maybe missed a negative earlier on in the question or something like that, so just check where it's gone wrong. So I've put a worksheet in our shared folder for you to work through on modelling differential equations. So if you could work through those, and then we'll go on to look at solving them after Christmas.